Swayam Prabha. Digital India. Educated India.
So, we will start with where we left yesterday. So, suppose I want to add so the sum bit here is 1. I am writing the carries. The carry that came from the previous stage is 0. The sum bit is 1 and the carry that goes to the next stage is 0. So, here again the sum bit is 0 and the carry that went to the previous next stage is 1. Here again sum bit is 0, the carry is 1, sum bit is 0, carry is 1, sum bit is 0, carry is 1, sum bit is 0. So, this is the answer, correct. If I add 1 1 0 1 1 0 1 1 with 0 1 1 0 0 1 1 0, I get this answer, okay. And these are all the carry bits. This is the carry in bit. This is a carry in bit that came from the previous stage, okay. So, so let us write the carry bits. So, 0, 1, 2, 3, 4, 5, 6, 7, C0, C1, C2, C3, C4, C5, C6, C7. This is 0, this is 0, this is 1, the remaining all are ones. Okay. So, this is the carries. If I know the carry at the earliest, and immediately I can compute the sum bit, okay, because your S0 is nothing but SI is nothing but AI exclusive or BI exclusive or CI minus 1, correct, or CI in this case, because we in our terminology we say this is 0, this is C0, okay, and this is A0, A1 and so on till A7, and this is B0, B1 to B7, okay. So, if I know CI, I can get SI immediately. So, how quick we calculate CI is the important problem. If I am going to calculate CI very fast, then I will be getting the sum bits correctly. So, what happens in the okay. So, what happens here is, first let us see 1 0 means what is the status of. So, we first calculate the status of the carries, which is called as the x vector, okay. So, we will calculate x0, x1, x2, x3, x4, x5, x6, x7. What is x0? X0 is it starts with kill, right. This is kill because C0 is 0. So, what is x1? X1 is propagate, right, 1 and 0. What is x2? This is generate. X3 is propagate, sorry. x4 is propagate. So x1, x2, x3, x4, x5 is also propagate. x6 is also, x6 is generate. x7 is propagate. 1, 2, so kill, propagate, generate, propagate, 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 propagate. So kill, next is propagate, next is generate, followed by 1, 2, 3, 4. 4 propagates. Then x7 is generate, then I have x8 is, okay. So then what I do, right, is this clear? So what is the time required to basically generate these x values? It's constant time, right? We just use one AND and OR gate for each. The AND will give you, so the state, so kill I call it as 0 0, but generate I call it as 1 1 and propagate as 0 1. Then basically I need one AND and one OR gate to generate these 2 bits. So in unit time I am able to find out these x values, right? Okay. Now I do what we call as the thing. So I do this operation. Okay, let us go back to this operation. I do this operation on the x. Kill with anything is kill. So kill with anything is kill. Generate with anything is generate. And of course propagate with propagate is propagate. Okay. So this yesterday we saw this table, right? I hope you have copied it. We will now go back to that. Okay. Now what we do here is, let us compute this y values. So y0 is x0, y1 is equal to x1 that star x0, y2 is nothing but x2 star x1 star x0 and so on, right. So if we start doing this, we will find that y0 is kill, y1 is propagate with kill, right. So this is kill, right, propagate star kill, right. Now x2 is, y2 is generate with propagate with kill. Just look at here, generate with propagate with kill. So generate star propagate star kill would be generate, right. Y3 will be P with G with P with K, so it will be G. Y4 will be again P with G with P with K, again it will be G. Y5 will again be G, Y6 will again be G, Y7 is G, Y8 is G. Correct? Are you able to follow? Is it clear? And what have we done here? If I am seeing a kill, my contribution to the next stage is 0. If I see a G, my contribution to the next stage is 1. Immediately I can decide, it is independent of this. If it is a propagate, then I have to go back to your right hand side, and if I encounter a G, then this is 1. If first I encounter a K, it is going to be 0, right. This is as simple as this, and that is what this computation mimics. Correct? Do you understand this? Now we see, after doing this prefix computation, if I see a kill, then it should be 0, the carry is 0, so C0 is 0. If I see a kill, so C1 is what? 0, C2 is 1, 1, 1, 1, 1, 1, 0. Okay? Sorry, 1, 1, 1, 1. Okay? So Now you see that there is a 0 0 followed by 6 ones, 1 2 3 4 5 6, and this is the last carry, this is this. Okay, you are able to follow? Yes.
Sir, isn't the calculation of y sequential again?
I am going to come to that. Okay, right. Now, are you able to follow my procedure? You are able to follow the procedure, and you are able to appreciate the correctness of this procedure. Now, if I am able to calculate these y values very fast, then immediately I will get that carry values. The moment I get the carry value, immediately I can generate the sum bits. So, my objective is, the moment I get these x values, how quickly can I compute these y values? Okay. Now, what is this computation? This computation of y, what sort of computation it is? x0, x1 star x0, x2 star x1 star x0, first class. It is a prefix computation, correct? It is a prefix computation, right? The next thing is, please note that this star is an associative operator. It is a semigroup operator. Star is a associative operator. For example, if I take this thing, let us say A star B star C is equal to A star B star C, correct? Let us put arbitrary values for A, B and C. Just tell me some random values. P, K, K. Okay. So, P star, K star, let us say G is equal to P star K star G. Now, what is P star K? K star G? K star G is G. Okay. K star G is G. P star G is G. K star, K star. No, we are doing it xj plus 1, which is okay. Anyway, whatever be. So, K star, K star G is K, and P star K is whatever way you want. You want this, which should be your left operator and right operator. So, A star B means A is here and B is here. Let us assume, right? Right? A star B means A is here and B is here. So, if I want to do K star G, K is here and G is here, so K star G is K. And if I want to do P star K, is going to be K. Now, P star K is K, P star K is K, K star G is K. Okay. Like this, how many combinations we will have? 27 combinations. So, there will be 3 possible values of A, B and C. So, 3 into 3 into 3. So, 27 combinations we can do, and we can verify that this is a associative. The moment I want to do a prefix sum on an associative operator for n bits, how fast can I do? Log n time. We have already seen that. So, in our previous slide, right, a prefix computation of n numbers can be done in, or n numbers or n elements can be done in log n step, provided the operator is associative. Please note that this star operator is associative, and hence we can basically do this entire thing in log n time, right. So, the moment I get these 2 bits, the A and B, in constant time I can generate the status, namely the x values, and once I have the x values, in log n time I can basically generate the y values. The moment I have the y value, then I can generate in constant time the carry, right. So please note that the yj will be only either k or g, each of the y's. Why? Because C0 or whatever x0 is k, and k with anything else will either land with k or g, right. The moment I have one k for sure in this, so the other y values, because I am doing a prefix computation, this x0 will be involved in all the computations, and the x0 will surely give a k. So surely p will not come, it will be either k or intermediately if you see a g, it will be g. So the y's that you calculate at the end will be either g or k, and it cannot be p. That is very, very important here. The answer for that is that x0 is k and x0 is involved in all your computations, right. Please note that x0 is involved in all your computations, and so the y values will be surely not p as seen from this table. If you see 1 k, then all the things will be k, right. So unless you see an intermediate g, that we have also seen in the example that we have worked out. So that is another important point that we need to take, right. So I'll give you the circuitry for a carry look ahead adder in the next slide, but now you understand how I can do carry look ahead addition in log n time, correct. So while a carry ripple adder takes n time, right. We will now give you the we will now look at this circuit for the carry look ahead adder. Is it clear? Are you able to follow, right? So much funda is there in building such adders, right. Many of the books says that you can do the carry will be computed in constant time, and they assume an n input gate. N input gate beyond is not possible, right. I can't have suppose I have a 128 bit adder, I can't have a 128 bit gate, right. Right, it is practically impossible, right. So this is the way we analyze a circuit, okay. This is something different, and so I just want to tell that point, right. There is a lot of, so you also would be dreaming, why did I do the discrete mathematics. So this is where it helps in designing circuits. One simple pointer that I could give you. Are you able to follow this? So this is the computation. So I do y0, y1, y2 till yn, and it is, this star is associative, and hence I can do prefix computation. That is what I am trying to tell you in this slide. So the way we will look at this, the first thing, when the A's come here, A0 to A8, right, when the A comes here, what we do is that we generate the kill propagate, or we first get the kill propagate or generate bit, that takes constant time, and that we give it into the parallel prefix circuit, right, and that parallel prefix circuit will give you the y values, will give you the y values. So I give the x values to the bits come in, I give the x values, the parallel prefix circuit will give you the y values. So here also there is an example, 0 1 means it is propagate, 1 0 is propagate, 1 1 is generate, 1 0 is propagate, 1 1 is generate, 0 0 is kill, 1 1 is generate, 0 1 is propagate, right, and nothing more here, okay. And of course the first C0 is kill. Now I give it to the circuit. So kill propagate will give me kill, so kill will give me kill, kill propagate will give me kill, kill propagate gives me kill, kill generate gives me generate, generate propagate will give me generate, generate generate gives me generate, generate kill gives me kill, kill generate gives me generate, generate propagate gives me generate. So the y values are basically output from this parallel prefix circuit. From the y values I immediately get the carry as 1 and basically generate the sum bits, okay. Immediately I could generate the sum bit. So in this case I am getting kill as the carry, right. So y0 is kill Kill means the carry is 0, 0, 0, 1, 0 XR 1 is 1. Here my carry is kill again, 0, 0 XR 1 is 1. So this is the sum bits as you see here. Now here I am getting kill, so 0 XR 1 is 0. Here I am getting generate, so 1 XR 0 is 0. Here I am getting generate, 1 XR 1 is 1. Here I am getting generate, 1 XR 0 is 1. I am getting kill, 0 1 1 is 0. I am getting generate here, so 1 XR 1 is 0. I am getting generate here, 1 XR 0 1, right. So this entire stuff, this part of the circuit takes constant time, order 1 time, that is constant time. This parallel prefix, as we had seen earlier, takes log n time, because we have n processing units, we will consider. So the total overall complexity of addition is going to be log n plus 1, or we can say some constant times log n. Okay, I think I have done it twice. I hope you all remember this. Okay. Now let us go and construct the circuit for this. So we use the recursive doubling technique that we saw in the class number 1. Okay, because this star is a associative operator. So what we do here? So we construct this entire unit, right? We don't. So what each of this unit will do is that it will compute that star operation, right? We can very quickly construct, a circuit for this truth table, right? So we can have what would be the truth table here? So I will have a truth table for xj plus 1 star xj, right? So I can say, so a star b is, so there is 2 bits for that. So I will have b1 b naught, a1 a naught, and whatever the output c1 c naught. Let us a star b equal to c, then I can construct a circuit very quickly for this. So kill means 0 0 0 0 0 0, kill star kill should give me kill, right, 0 0. Propagate star kill should give me kill. So propagate is what, 0 1 0 0 should give me 0 1, right. I have all the 16 combinations and the 16 combinations and the 2 outputs here. So I can easily construct a circuit which will compute this star with a truth table, right. I leave it as a very simple exercise. It will turn out to be a simple AND OR combination. Okay. So I can write all the 16 combinations here, do Karnaugh map, and get the circuit for this. So what we see in each of this block is a circuit which will take two status like kill, propagate, or kill, generate, and then it will compute the new value, the star operation. So what happens here? So this is the first level, right. In the first level, what we do in recursive doubling, we compute with the nearest neighbors. So propagate star kill will happen here, right. So propagate star kill is kill, propagate star propagate is propagate, propagate star generate is generate, generate star propagate is generate, propagate star generate is generate, or yeah, correct, and generate star kill is kill, kill star generate is generate. In the next stage, I have to go 2 away, right. Here I am 1 away, I have to go 2 away. So what I do? Kill star propagate is kill, kill star generate is generate, propagate star generate is generate, generate star generate is generate, generate star then generate star kill is kill, and so on. And next time I am going 4 away. So at the end I get this whole prefix computation, right. In the case of the addition we saw, we were reusing the same unit here again and again. right. Still we will do it off in log n time, but I do not want to reuse this, I am replicating this unit for, so since I want to do an 8-bit addition, then at least I need 3 stages, log of 8 is 3, right. So I am replicating this 3 times and showing, but I can reuse the same unit again for the star, right, but then I need multiplexers to keep routing it. So this is very easy for me to do, but there is another advantage of doing this also. But please understand that if I have such an organization, this is basically not a computer program, right, we have to do it in hardware. So I just realize it as this array of those star computing units, and each computing unit I connect it in such a way that at the end I am getting the prefixes. The moment I get these prefixes, from this I know that the carry is 0 0 0 1 1 1 0 1, which I will again XOR with the respective sum bits, respective input bits to get the sum bit. Is it okay, right? So the construction of this circuit essentially goes with the way we have described the recursive doubling in class number 1. Are you able to follow? Yes or no? Now what is the advantage? See, in the case of the recursive doubling that we saw earlier, we were using the same unit, again and again to compute the next stages, right. But now in this case, are you able to follow what I said just now? In this case I am using the same unit, the same unit was used, this is a start, the same unit was used in step 1, the same units are used in step 2 and step 3 and so on. But in this case I am not using the same units, I am just replicating the units. I have a lot of real estate in my chip, right. Today a transistor size is, if I assume roughly a transistor is a square, the edge of the transistor is 14 nanometers, 14 into 10 power minus 9 meters. So I could put billions of transistors, so I do not mind putting some. So what is the big advantage of this? Less processing power. I am doing that processing. So I have improved the area, I have increased the area corresponding to a carry ripple adders. Please note that the area is now bloated up, okay. And since the area is bloated up, that means I have put more transistors, so more transistors will be toggling 0 to 1 and 1 to 0, that means more power is also consumed. So I have increased my power consumption, I have also increased my area consumption, but I am getting a good timing performance, I have decreased the execution time. But what is specific advantage of having something like this? So suppose I want to add a 128-bit number, it takes 7 units of time here, right, 7 plus 1 unit, 7 plus 2, 9 units of time, correct. Do you get this? Now what will happen here is that I can do something called pipelining. So I am introducing pipelining at a very early stage, right. This is we will do pipelining in the case of processors also, CPUs. How are we going to do pipelining? We will go and discuss that as we proceed in this course. But please note that I can do a pipelining. So what we see as this this red, this yellow, green and pink, these are storage, these are all registers, okay. So the first set of data will come and you calculate this first stage and you store the results. When let us call this as stage 1, stage 2, stage 3 and stage 4, okay. First set of data comes to stage 1, you compute that and store the results here. And you also take along with it your A's and B's also, you just keep propagating. So this not only stores the result of this computation, right, understand, but it will also take along with it the A's and B's. Now when in the next stage, when the stage 2 is computing the results of stage 1, I can bring in another 2 set of new numbers. When the first pair of numbers are in stage 3, second pair of numbers could be in stage 2 and the third pair of numbers could be now in stage 1. This register or the storage I have put will isolate these stages so that some computation happening there will not actually come to the next stage, because the registers get updated only in the clock pulse, right. So, I hope you remember what is a register, flip flop and registers, right. Okay. So, the register basically gets updated only when there is a clock pulse. So, first set of data gets processed and stored here, then the second stage will start working on the first set of the first result. Now, the second set of data can be processed by stage 1, while the first set of data is processed by stage 2. And the processing that happens here will not change the inputs to the second stage, because I have registers here and the registers will not change until it sees a clock pulse. So, the results are stored for computation by stage 2, and that result will get saved in the green register. So, when the first set of data is processed by stage 3, the second set of data can be processed by stage 2, and the third set of data can enter stage 1. First set of, and the result will be stored in the respective pink, green and yellow at the next clock pulse. And again, when the first set of data is processed by S4, second set can come to S3, third set can come to S2 and fourth set can come to S3. By this, I can keep adding numbers one after another very fast. So, if I want to add 8 different numbers, suppose I have a program in which there are 8 number additions happening immediately one after another. The first number will come after, first answer will come after 4 cycles. The second answer will come off in the 5th cycle itself. The third answer will come off in the 6th cycle and so on. So, in the first answer it will take 4 cycles. So, that we call as the initial latency. The word that we use is latency. This is the latency of the pipeline. The second answer will come off immediately in the next cycle. Third answer will come off in the next cycle, and fourth answer will come off in the next, and so on, right. So, what is the cycle duration? So, if I do not have these registers, then the entire computation should happen in one cycle. Assume that each takes 1 unit of time, the cycle duration would be 4. Since now I have put this thing, so in each cycle I am expected to do only one operation, right. I am so my cycle now time which we required 4 in the absence of the storage, now it will become 1, right. Correct? Are you able to follow? If I am going to do the entire operations in one cycle, then the circuit depth here is 4. Remember, this is a good topological sorting here. I can remove the first stage, second stage, third stage and fourth stage. So, the circuit depth will be 4 if I do not have the storage. Circuit depth is 4 means my cycle time would be 4. That means my frequency will be 1 by 4, 0.25 whatever. Now, what is my cycle time? It becomes 1, right. So, my my frequency also becomes 1. So, the frequency actually gets multiplied by 4. So, if I would have run with 500 megahertz, I could now run with 4 times it, 2 gigahertz. You are able to appreciate this, right. So, by pipelining, what is happening? My frequency actually increases multifold. Frequency of operation of the circuit can improve multifold. And what happens? I am not only working at 2 gigahertz, but at the end of every cycle, I am going to give you one answer, except for the first fellow. First fellow will take 4 cycles, but after that, every cycle, provided I have numbers to add. Suppose I have 1 million numbers to add. So, what would have taken 1 million into 4 cycles, 4 million cycles would have been the total time requirement in the absence of this pipeline, right. In the presence of this pipeline, first fellow will come at 4, second fellow will come at 5 and so on. So, 1 million plus 4th cycle I would get all the answers. So, it is not that my frequency has become 4 times, my execution time also, or what we call as the throughput, number of numbers that I could add within some unit time, that is also become 4. So, this is a very big advantage that we get by pipelining. You understand this, right? So, the basics of the intuition for pipelining comes because when I do not have these storage stages, after this first stage finishes processing the data, it waits for the remaining 3 cycles, right, for the entire computation to finish, right. Unnecessarily it is holding the data, correct. And similarly, when the first, third and fourth are processing, right, the second one actually is idle. When the data enters here, assume there is no storage, no pipelining, when the data enters this part, the second fellow is simply sleeping, it need not do anything, and then it process, then when the third and fourth are doing something, the second fellow is just keeping quiet. So, every stage that we look here or every level that you look here is not doing any useful computation when the other levels are doing some computation. So, when a data enters, all the 4 levels do some computation, and when the level k is performing the computation, all the remaining 3 levels keep quiet or they do not do anything sensible there. Either they are maintaining the value or they are just idle. So, that is something. So, that is something we have exploited to see that we get this pipeline behavior. Fair enough? Did you follow? Any doubts? Okay. So, the depth of this circuit has reduced from order n to order log n, correct. But the size is still order n, not exactly order n, but some constant times n, right. And this results actually in a very fast order, okay. This results in a very fast order, okay. Why is the circuit still order n? But see, I am having log n stages, each have n hardware, so it should become n log n, right. No, I have, this is log n stages, each stage I have n, so let us say it was 8, right, to start with. This is log n stages now, so it should be 8 into 3, right, 24 units we have, 32 units we have, right. So, it should be n log n in some sense. Average, what do you mean average? I am realizing the circuit. So, I go and say that the circuit is still order n and I am not wrong. Why? Can you just carefully look into this and tell me? So, in stage number 1, please note, somebody got the answer. See, what pipelining?
Like effectively it becomes like only one layer at a time is being used by each edge.
No, but I am saying size of the hardware is n. I am going to put the transistors here, right. So, please look at this slide, right. You have 24. Yeah.
Log n numbers with n log n steps. So for each number it's effectively n size.
No, the size is n log n. Do you appreciate this or not? I have log n stages, each I have put n fellows here. Yeah, tell me.
There are some unused blocks.
Exactly. So please. So here please see here that this block is not used at all. This is just a storage. So at the first stage I can remove of 1, the second stage I can remove of 2, the third stage I can remove of 4. These are all unused, right. It's just storage element. I just have to push this. Correct. So this essentially means that, so first stage I have n, right. I remove 1, second stage I remove 2, third stage I remove 4, right. So now if we could compute this sigma, right. So this will be n into log n minus 1 plus 2 plus 4 plus till n, right. So when you compute this we can show that this is order n. Right. So we can still get this to very close to order. right. So if you calculate from the back, right, this will be 1 plus 2 plus 4 plus till n. So what is this? What is 1 plus 2 plus 4 plus till n? 2 power log n is n, right? So what is 1 plus 2 plus 4 plus? 2n? 2n minus 1, correct? Are you absolutely sure? Hey, what is this? Correct? Okay, right? So that is something that you need to be extremely careful while designing circuits. Okay, right? Okay, so so we'll meet again on Monday. So kindly revise these things. So Monday morning 10 o'clock. So we will continue with carry save addition. Okay, thank you.